Hey, fifth lecture, chapter 2. And yes, I'm wearing the same t-shirt as I have for the last 3 lectures. Every now and then, a day, I get a chance to do a few of these together. So this is one of those days for me. And plus, I'm trying to get ahead of you guys a little bit so that nobody's waiting for me to do lectures. So trying my best to stay ahead of you guys. And here we are, fifth lecture, chapter 2, talking about the scientific method. And this time, we're going to talk about correlation. We're getting closer now to that understanding why something's happening, but we're still not going to get there. Correlation is sort of a step between those first methods we talked about and then the experimental approach, which is really going to be, the ultimate way of getting at the truth. Remember, this is all about seeking the truth. The correlations will tell us a little bit more than the previous stuff in the sense that it will focus on how 2 variables are related to one another. And so we will get to know if variables are related, and we'll learn a little bit about that relationship. But we're still not really going to understand what's driving it all. But still, it's an obvious thing we like to do along the way to understand a set of data, and we're going to talk about it today. It's got some cool stuff, and it's important because if we go back to that very first, remember at the very first year I was talking about these studies suggesting that drinking coffee may help you live longer. They were all typically correlational. Okay, what they show is the more coffee per day somebody drinks, the longer they tend to live. So as coffee drinking goes up, life expectancy goes up. We're going to be talking about relationships like that. You hear about these all the time in the media, and there's always a temptation to assume causation. Causation is going to become a big word. That is, when most of us hear that, people who drink more coffee live longer, what we actually hear is coffee makes you live longer. So we assume a causal relationship, that it is the drinking of the coffee that is causing those individuals to live longer. Okay, well, what if I'd said something different? What if I'd said to you, okay, I can't just do it right off the spur of my mind. I can't do that right away. So anyway, let me just say, by the end of this section, I hope you'll realize why that conclusion that coffee causes you to live longer is not necessarily warranted. And we'll come back to the issue with drawing that conclusion. But this is the problem. The media tempts you to draw that conclusion, and you have to be scientifically literate enough to say, hey, wait a minute, that's a correlation they're telling me, right? Aren't there other possible explanations for what I'm seeing? And there are. And so that's what we'll talk through. Okay. So first of all, what is truth by association? That's kind of weird. Truth is not a good word there. Bad, Steve. I shouldn't have used that word, truth. I don't know. Really, correlations are about associations or relationships among variables. Actually, relations. I had a academic supervisor in the past tell me that humans have relationships, numbers have relations. I don't know if that's a generally accepted truth, but I stick with it to this day. So correlations measure relations. And so what they're actually doing is you take a pair of variables, 2 variables, and the question is, as one of those variables gets larger, so in certain individuals, let's be concrete. Let's say one of the variables is age, and we have a group of people, 50 people. And so that'll include some young people and some older people. So imagine we've measured all their ages. We've also measured something else about them. How much coffee they drink a day. We'll go back to coffee. and so we can ask, as age goes up, as we compare younger to older and older people, is anything systematic happening with coffee drinking? Is their coffee drinking also going up as they get older? Or is it possible that their coffee drinking is going down as they get older, right? Let me give you a better example of the second one. Maybe if instead of coffee drinking, we talked about how many nights a week do they go out socializing, right? When you're young, you do that quite a bit. As you get older, you do that less and less. So that one, as you get older, you drink less and less coffee. We're going to call that a negative correlation, because as one variable is getting bigger, the other one's getting smaller. We'll do these scatter plots in just a second. But the other ones are positive correlations. If age is getting higher, and let's say coffee drinking is going up, you drink more coffee the older you get, that would be what we call a positive correlation. So the first thing to kind of get, and the textbook emphasizes this too, these words positive and negative, they don't mean good and bad. That they're charged words, right? They can mean good and bad, but in this case they don't. All it means is, are the variables changing in the same way? As one gets bigger, does the other get bigger? Or are they changing in opposite ways? As one gets bigger, the other gets smaller. By the way, there's also the example that as one gets bigger, the other one doesn't do anything systematic. Sometimes it gets bigger, sometimes it gets smaller, and we call that no correlation. There's just no relation between those two. Okay, so let's just sort of slowly walk through these graphs, and then we're going to do a little bit of hands-on, and I'm going to encourage you to do the same thing so that you can really start to feel this at a sensical level. It can just make sense to you. So this is a scatter plot. And so let's say we were looking at somebody's height versus their weight. Okay, and we might expect, I have to give you the thing that'll let you never forget something. When we talk about graphs like this, we sometimes talk about ordinates and abscissas, like the x-axis and the y-axis. One of them we call the ordinate, one of them we call the abscissa. Can you remember which one's the ordinate and which one's the abscissa? Here's a little mnemonic that'll help you remember it for the rest of your life. Literally. Look at my mouth and look what happens when I say the words ordinate, abscissa, ordinate, abscissa. I'm exaggerating, obviously, but when I exaggerate, ordinate, what's my mouth doing? It's going this way. Ordinate. What about abscissa? Abscissa. It's going this way. Ordinate, abscissa. This is the ordinate. This is the abscissa. Okay? X, Y. And so on the X or the abscissa, let's say we have height. And on the Y or the ordinate, let's say we have weight. And then every X is a person. Okay? This person, I'm going to come back to that. I'll come back to that example. This person has this height and this weight. So we put the X on a spot that reflects their combination of those two variables, right? How tall are they and how heavy are they? Here's somebody that's taller and heavier. All right? Here's someone that's shorter and lighter. And so this allows us, when we put these on here, this allows us to see the relation, right? And we often will sort of put a line against it. We'll kind of like draw a line through it because we're looking for what are called linear relationships here. We're looking to see if they go up in this way. And so you can see that cloud of dots, you can plot the line, and you notice this line kind of is going up and to the right. That's what positive correlations do. So as height is getting bigger, weight is getting heavier. Right? The taller somebody is, the more they weigh. And so this person is the tallest in our sample. They're not the heaviest, by the way. This one's heavier, right? A little less tall and he's heavier. So it's not what we call a perfect relationship. But it's a positive correlation. So generally speaking, the taller somebody is, the heavier they are. And we see this sort of pattern in the scatter plot. And if we fit a line to it, it would show this sort of upwards, up and to the right slope. The negative correlations, again, we could have this, but if this is height and weight, this would be really weird, right? Because the taller somebody is, the lighter they are. Like, sorry, my Mac is very sensitive, so it jumps around back and forth. That wouldn't make a lot of sense, but in other cases it will. Let's talk about one of those other cases. Let's bring this up. So just to kind of, as you've been thinking through this, let me ask you this question. Let's imagine we're talking only to women. And we're going to look at two variables, but we're going to look at them at different points in their lifespan. Okay, so the variables will be how tall they are and how physically attractive they think they are. A self-rating of physical attractiveness. Okay? let's start by imagining we do this when the kids are around 14. Why did I pick around 14 or 15? That's the age when a lot of girls go through puberty, and they tend to go through puberty first before males do. So the females go through puberty first, and of course they grow tall, right? We all do when we go through puberty. But the boys haven't gone through it yet. So when we look at 14 or 15 years old, that's the time when sometimes a lot of girls are a lot taller than a lot of the boys in their school. If we asked girls at that time, how tall are you and how attractive do you think you are? What do you think the relation between those variables would be? Positive or negative? Do you think the taller girls would feel more attractive at that age or not? What if we asked them when they were 20 years old? Would the relation change? So I'm going to suggest it would. I'm going to suggest that when they're 14, come on over here, we might see something like this, a negative correlation. Why? Well, because sometimes girls can feel kind of like ogres at that time. They're growing big. The guys are small. You don't want to dance with a guy because you feel like you're this big whatever. And the bigger you are, the taller you are, the more you have that kind of feeling. So you might feel like I'm ugly, like I don't like how I look at that age. But of course, if we asked at 20, so okay, let's go a little slower. So what would we see here? The taller they are on the abscissa, the less attractive they would rate themselves. So the short ones would think I'm pretty attractive. But the taller the girls would say I'm not so attractive. That would be a negative correlation. But by 20, now the boys have gone through puberty as well. And now the boys tend to be tall like the girls. At that point, we might see that the taller the girl is, the more attractive she feels. Even the tall girls don't tend to be as tall as well, they can be taller than some of the boys, but they're still shorter than a lot of the boys as well. On average, the girls are shorter than the boys is what I'm saying. And so by that age, it might be that the taller the girl is, the more attractive she feels. Okay, so just a good example for thinking about what a relationship represents, and what a negative is, what a positive is, and what no correlation looks like, which is just neither clear pattern, right? Just a mess of dots. So there's one thing I want to recommend. I'm going to skip out of here, and I just did a search for correlation generator. Okay, and I found, I'm going to come back to the spurious correlations in just a second too, but I'm going to go to this one, Pearson correlation coefficient calculator. Shows you the formula for a correlation. If you ever want the formula, there it is. But you don't need the formula. You can just go to the calculator, and you can create some values here. And so you can imagine something. So let's imagine we're doing how much coffee somebody drinks, and we ask a bunch of people. And we find this first person has 4 coffees, this person has 6 coffees, this person has 2 coffees a day. These people don't have any coffee a day. Somebody else with 2, got a few 1s, few 5s, few 6s, a few heavy drinkers there, another 3. Okay, so I just produced these. So these are all individuals, and this is how much coffee they drink. So we could ask something else about them. We could ask, what's their score in their midterm exam? How did they do? And I'm going to generate things just sort of randomly for this. And so I'm going to say things like, I don't know. I'm not going to try to build a relationship at all. I'm just going to kind of put some random grades that students could get on exams. Here's a really good one. Just trying to make sure I have enough to have it covered, the same sort of spaces. There we go. Okay. So right now, this would be a situation we can just say, okay, let's calculate the R. Let's see what we got. So here's a scatter plot. So first of all, the nice thing about this is you can actually now kind of say, okay, I'd like to see this person. 467. Where are they? I think because we went out to 5 or 6, so I think it's this person. They don't have any values on this, but I think that's this person. The number 1 person with 4 and 67 would be this person. So you could see first of all that every one of these dots kind of reflects one of these pairs of numbers. Okay. Here's all the fancy math stuff that leads you all the way down to, well, what's it lead you down to? This. Well, I don't know what the meta, that's kind of weird. Cross-check, I don't know what that is. But this is, oh, I guess this is the final. I'm just looking for the final R value. They've got all these sorts of things. Okay, this is the final R value, I guess. What the heck is this R value? Oh yeah, there it is down there as well. What the heck is that value? So we can actually compute how strong the relation is. And so I'm going to do this in front of you so that you'll get a sense of it in just a second. But right now, this is pretty much zero, right? Minus 0.01. It's pretty close to zero. And that's because I just entered numbers randomly. So it would be weird if there was any relationship between those two numbers, because I just entered exam scores just semi-randomly, and coffee. And so we wouldn't really expect any relationship. But now let's build a relationship. Let's build a positive relationship. And so let's say those people who got a lot of coffee, well, let's start with the people that didn't drink much. And let's say they didn't do very well, the people who didn't drink much coffee. So I'm going to put them in the 54s. Here's a 1. Maybe we're going to give them a 60, so they did a little okay. This one I'm going to give a 56 because they didn't do so well. Now, these people who had a lot of coffee, I'm going to pretend that they had really high marks now. I'll do somewhere in the middle here. So I've kind of created a situation. Now let me go recalculate. Notice now these dots are more lined up. We're starting to see that hint of a line. And you should be sensing that this is a positive correlation. Okay? So when we go to the R number, we're going to see a positive number, first of all, because the line goes that way. And what's it going to range from? Well, a perfect correlation is 1. Okay, 1 means as one thing goes up, the other one always goes up. Now, correlations aren't usually perfect. There's usually a little bit of not that going on in the data, and that's what we see here. But this is a very strong positive correlation, okay? The negative or the positive, again, is only about the direction. Whether, as one goes higher, the other one goes higher. So let's build a negative correlation. Okay, so a negative correlation would mean that when you had a lot of coffee, that made you not good at the exam. So let's take these people who didn't drink much coffee, and now let's pretend they did really well, and give the low coffee drinkers pretty good marks on this. And let's do some of these high coffee drinkers, and let's say they didn't do well at all. So there's a high. Here's a couple of highs. Okay, so you see what I'm doing, and maybe I'll just make this more middle of the road, because he's a middle of the road coffee drinker. So now if I go calculate this, what we've got is a bit of a negative going on, right? If you saw a line, it would look like it's going down and to the right, which is a negative correlation, which means as the Y values get bigger, number of coffee drank, this one gets smaller, the grade on the midterm. And so if we go down here, look, we have a negative correlation now. And it's again sort of close to 1. So correlations range from -1 to +1. 0 means there's nothing happening. But as you get closer to 1, that means there's something happening. Those two variables are related. And the sign tells you whether it's a positive correlation or a negative correlation. Okay, so the number itself tells you how strong the correlation is. The sign tells you whether it's negative or positive. So that means if I gave you two correlations, if I said, here's one situation where these things are correlated, and the correlation is minus 0.6, and I said, here's this other one where there's a correlation and it's plus 0.4. If I then said, which correlation is stronger? Which relationship is stronger? What would you say? It's the first one, the minus 0.6, because the strength is about how close that number is to 1. The plus or minus is just about the direction of the correlation. So, so the minus 0.6 is a stronger correlation than a positive 0.4, even though the positive 0.4 seems like a bigger number on the number scale kind of thing. Is that cool? I hope it's kind of cool. Okay, let's jump back to here now that we've done some playing. And I would just suggest you play with that site. The more you get your hands dirty and play with numbers, the more comfortable you'll be with all this kind of stuff. Okay, so now let's talk about the temptation of causation. So here's some data. And it's a very, this is real data. And so we've gone to a bunch of countries and we've asked how much animal fat do they eat? And so I'm from the Netherlands culturally, by the way, and the Netherlands eat a lot of animal fat. Now this actually says Canadians eat more. I find that surprising because the Netherlands eat meat for breakfast, lunch, and supper, often with cheese and dairy. Cheese is dairy. So it seems weird. Apparently New Zealanders eat the most animal fat intake. And then down here we have places like Thailand and Japan and Taiwan where they don't eat nearly as much animal fats. And then over here we have the age-adjusted death rate. So basically how soon do they die? What's the rate of death? And what you're seeing here is a positive correlation, right? The dots, scatter plot, dots all line up there, which again really tempts you to want to say, eating high-fat food kills you, makes you die earlier. That's one possibility. So when we talk about this causation temptation, it's not that you're necessarily wrong when you leap to that causal inference. That's how we would talk about it. When you end up thinking that's what's true. The problem is there's always alternate explanations that you have to consider. So let's do this one to start talking about this problem of causation. So this table is presenting you some numbers that show the correlation between the students' grades in a course and the teacher ratings, and how well the students rate the teacher. And you see across courses it doesn't really matter. We're seeing positive correlations, sometimes pretty strong positive correlations, right? These 8 ones are pretty strong. What does that mean? Does it mean that students who did better in the course like their teacher better? Or does it mean that students who like their teacher better do better in the course? What is actually driving it? Are the good grades making you like your teacher, or the good teacher helping you get good grades? You don't know. Those are two different possible causal stories, and the correlation cannot tell the difference between those two. Very often we don't know. And it's a little, when it's meat consumption and dying, you think, well, okay, dying doesn't cause you to eat more meat. So in some cases, you can't sort of go back and forth. But in many cases you can. Many times when two variables are related, you don't know if the first one's causing the second one to change or vice versa. And worse yet, there could also be what we call a third variable that's sort of causing those first two to be related. So here's my favorite example. I am tall, by the way. You don't know from this way of talking, but I'm 6'3". So I'm a relatively tall guy, and I always like these sort of stories that suggest that, hey, you know what? The taller you are, well, in this case, the more money you make. There's a correlation between height and estimated income. In fact, every inch seems to give you an extra $800 in increased annual earnings. What's going on there? It could be that being tall is causing you to earn more. Maybe people, when they have high-paying jobs, for some reason trust tall people more, feel more comfortable hiring the tall people into those jobs, in which case your height is very directly earning you money. Now, it could also be that when you earn a lot of money, you're able to eat really well and reach your maximum height capacity. So maybe it's the money earning that's making you taller. That one seems like a little more stretch. But here's a third possibility that a lot of people believe is true. Your socioeconomic class. So you're born into a family, and that family has certain attributes or whatnot. How am I gonna connect this up? Yes. And so a richer family has more money available to it. They also tend to have more connections to other rich people Okay, so if we think of the first one, the fact that they have more money, well, if you're born into that rich family, you're probably going to get better nutrition as a child because they're going to have the money to give you good food. And that higher level of nutrition is going to likely help you reach your maximum possible height. Also, by the way, as you're growing up and looking for jobs, it's who you know, right? And if you're in a family that's well connected with other potentially rich people who might potentially offer you a job, then you might be able to get a higher paying job simply because you're from a richer family. So being from a richer family could cause you both to be taller than average and to make more than average. So it would look like the tall people are making more. They are, but it's not because they're tall. It's because of some third variable here, financial benefits, that make them both tall and give them opportunities to earn more money. That's the problem with correlations. We don't know what's causing what. So they're very interesting to let us know, okay, those two things are connected somehow. And that makes us want to know more. And that's going to take us to experiments. Okay, so let's leave the correlations here and play with that. I just remembered there was a spurious correlations link there I was going to touch on, but I don't think I will. Check it out yourself. Click on that, read it. It's kind of funny. It relates to some of the stories they tell you in the textbook too about eating ice cream causes murder rates to go up. Check that out. That's another what we call spurious correlation. It's caused by something else, a third variable. So check those all out. Come on back, and then we'll finally get to experiments, which is where the action really is. Okay, talk to you soon. Bye-bye.